I'm not gonna do the audio sharing then. Anyway, okay, can you see my presentation?
Yes, we can. Does your presentation have any audio?
Yes, but it's of secondary importance. So feel free to download then the presentation, and then you can experience the full version. But for now, let's stick to the visual only. All right, so first of all, I would like to thank the organizers of the USERN for inviting me again. Obviously, it's a special place in my heart because of the fact that I won the inaugural prize. But I'm very honored that you keep inviting me back. So thank you very, very much for that. So let me start with the lecture then. So a quick bit of background about myself. So I'm based in the Netherlands, in the heart of the Netherlands, you could say, in Utrecht, which is a bit south of Amsterdam. And I'm based at the Faculty of Medicine. And it's one of the largest university medical centers in the Netherlands. Around 12,000 people work there. So it's like a small village, or small city, I should say. And it consists of many divisions, and one of these divisions is the imaging division, hence the background image that you're probably looking at, the brain image. And within this imaging division, we've got many departments, and within the departments, we've got research groups. And one of the research groups is mine, which is called the ProVideoLab. And we mainly focus on processing, analyzing, and visualizing diffusion MRI data. And I'll come back to that in a moment, what diffusion imaging is. And so, like I said, I'm based in a faculty of medicine, but I'm a physicist. So I'm the nerdy person in the department. And so what I basically do is, I do the coding, the math, the physics. But in the end, I'm doing diffusion imaging. And the nice thing is working at a medical facility is that there's a lot of interaction. And so the clinical people often have questions and ask whether I can help out, whether diffusion imaging can help out. And vice versa, if I'm developing something new, it's always nice to have, let's say, an audience or people that I can tap into it to say like, hey, is this something that can be useful to you? All right, so when I'm discussing diffusion imaging with medical doctors, to them it's often considered as the kind of confusion imaging. Something that I'm kind of very aware of, that this kind of matter is kind of difficult to understand. So what I'm going to do now is I'm going to give a first crash course on all the concepts related to my title. And let me start with the brain, okay? Because diffusion MRI to study the brain, well, I'm going to be very brief because most people know a bit about the brain. But if you, let's say, cut it open, then you can appreciate different tissue types. You see this kind of dark area, we call them the gray matter, it's the cortical regions. And then this white region is called the white matter. These are, let's say, your cables, the fiber connections, linking the different brain regions. And then there's the, the fluid, the cerebrospinal fluid, which surrounds the brain. But my focus today will be on the white matter, the cables, the connections in the brain. And if you look at this image, this Klinger dissection, you can appreciate this kind of fibrous structure. First thing you can think of is, let's say, spaghettis. So it seems like the white matter of the brain acts like big spaghetti bundles connecting the different brain regions. And you can literally think of this as kind of, axonal fiber pathways, these kind of cylindrical objects, these constituents, myelin sheets wrapping around the axons. Then there's a quick note about MRI. I think, if I'm not mistaken, around 7 Nobel Prize winners have been working on MRI. So it's, let's say, an important field of research. The last ones were Lauterbur and Mansfield for their contribution to medicine, actually. And so what is MRI? Well, people also tend to know this. You've got a big magnet. And when you go into the magnet, you can look at the inside of the body. And if I show you these images of the brain, you're probably familiar with these. If not through medicine, it's probably through James Bond movies or CSI or whatever. So, you can look at different tissue types because they've got different relaxation properties. And this is all very nice, but if you look within the white matter, you're not really, you don't really know where you are within the white matter in terms of the orientation of the fiber pathways. But I'll come back to that in a moment. One quick thing to realize is that with MRI, if we zoom in and we look at really the building blocks, think of a pixel in 2D, but in 3D a voxel, then we're not looking at the scales that some of these neuroscientists are looking at in cell biology. They're looking at micrometers. In our case, with MRI, typically in vivo, we would be looking at the order of 1 to 2 millimeters. Okay, so these are the huge building blocks. I mean, the good news is with MRI, we're doing this in vivo and non-invasively. So that's our strength, if you want. We don't have to kill the subject to image it. Okay, and then there's the concept of diffusion. Well, what is diffusion? Well, if you think of a glass of wine and you just let a drop of wine, drop in this glass of water, these molecules, they spread out, right? And the microscopic phenomenon that you observe after some time is that all the wine molecules have diffused into the glass, right? From a microscopic point of view or molecular point of view, diffusion can be considered like this. I'm showing this animation, the two pools of particles, red ones and green ones. If I remove this white barrier, you can now appreciate that as all these red particles, they move around and they bump into each other due to thermal energy. All these molecules, all these little particles got energy, and so they're moving. And it's due to this kinematic energy that they're mingling at the microscopic level. And at some point, you can appreciate that all these particles are like intermingled, and then we have some specific diffusion rate, etc. And this is something that we can compute. This diffusion process was first observed by Robert Brown, an old botanist. I think it was Scottish. Anyways, it's called Robert Brown. That's why we call it a Brownian motion, this erratic motion. As you can see, he was also very, very excited with his discovery there. Happy chap, always fun at the bar. Anyways, we call this Brownian motion. And there's different types of diffusion. Isotropic versus anisotropic diffusion. Typically, this is kind of the reaction that people give, like these different difficult words, but I'll explain them with an animation. Isotropic diffusion. Well, again, I'm showing you the red particles in the middle. And when I start the animation, you can now appreciate that the red particles are moving along different orientations with the same speed. This is what we call isotropic diffusion. So the same amount of diffusing speed in the different orientations. So you can think of it as, let's say, in 2D, a circle growing with the same rate in each orientation. In 3 dimensions, you can think of a sphere. Anisotropic diffusion, by contrast, the opposite of isotropic diffusion, basically refers to the fact that there's a pronounced preference in diffusion orientation. So for instance, if you've got barriers like these horizontal lines, these dashed lines, then it's not hard to imagine that these red particles, like shown in this animation, are actually spreading out more pronouncedly horizontally than vertically. Okay, and this is what we call anisotropic diffusion. And again, you can visualize this in this case then with an ellipse in 2D or in 3D with an ellipsoid. Okay, so this is kind of the process of diffusion characterized. I'm not going to go into the math, but there was a very clever guy called Einstein who came up with this diffusion equation. He said that the average spread of the particles is proportional with the diffusion coefficient with time. All right, then let's put some things together. Why diffusion in the brain? Why looking at, why looking at diffusion in the brain to begin with? Well, the brain, it has a lot of water molecules. 80% in brain tissue consists of water molecules. They also have energy because they're at roughly 37 degrees, so they move around. They bombard the environment. They probe the environment. And so it's not hard to imagine that these water molecules also diffuse anisotropically, meaning these water molecules, they will diffuse more along fiber pathways than perpendicular to them because of barriers, right? These molecules, they will bump into their surrounding tissue, not with other molecules per se, but with their surrounding tissue, which technically is also molecules, but they're fixed. They're not like moving around, etc. But these water molecules, they will move more along the pathways than perpendicular to them. So it's not hard to imagine that we also experience this diffusion profile being anisotropic in the white matter. Okay. Let's put it all together then. So we're looking at diffusion, we're looking at MRI, we're looking at the brain. What we're basically doing is looking at MRI data like here. So for instance, in this case, we see on a conventional MRI image, the white matter, the bright part in the image, okay? But we have no idea about the orientation of these fiber bundles, right? But if we have access to diffusion information and we can defer what the orientation is of the diffusion, then we can make the assumption that this is due to the organization of the underlying pathways, okay? So what we do in practice is we acquire MRI data along many different orientations, looking at the amount of diffusion in many orientations, and by getting that information, these kind of projections, we can go back, we can calculate back what the three-dimensional diffusion profile is. And by doing so, we can basically model for each voxel, for each pixel, three-dimensional pixel, we can model the three-dimensional orientation of the diffusion. If you do that, then we get an image like this, right? So it looks kind of like a candy store, right? All these M&Ms, but these are basically ellipsoids describing the Gaussian diffusion process. Here's an axial slice. Reason why I'm showing this in more detail is that in practice, we don't show these ellipsoidal maps to medical doctors or biologists because it's kind of cluttering, it's cumbersome. But if we reduce it to a map like this, then it makes more sense to understand. So the color is the same. So here we can see all the ellipsoids. Color is the same, but the brightness is reflected now by the underlying coherence, the cigar shapeness of these ellipsoids. So the more elongated the ellipsoid, the more the underlying structure shows coherence of orientation. Okay, so what about the colors then? Well, the colors here reflect an orientation. Everything left, right is color encoded in red, everything front to back in green, and everything up, down in blue. So what I'm showing you now is an animation where I'm overlaying the diffusion color information on top of a T1 weighted MRI image. So this conventional MRI image clearly shows the interface between white matter and gray matter, but within the white matter, you come kind of blind in terms of the orientation of the underlying pathways. But here, we can clearly see that here we're looking front to back in green, and here it's more reddish, left, right. Think of the corpus callosum connecting two hemispheres. In the middle, it's clearly red. Here it's kind of arcing to the front, and you get a green color. So by just looking at these color maps, you already have a good idea of the underlying organization of the fiber pathways. But it's a very powerful technique because also if you have that color information in terms of orientation, you can look at the white matter and see whether something is abnormal or not. So in this case, if you look at this image, within the white matter, within the corpus callosum, on a T1 weighted image, it looks very uniform, looks very normal. But if you look at the color encoded diffusion map, you can clearly see this kind of green patch in the middle of red. Red means left, right. This is the corpus callosum connecting both hemispheres. It goes left, right. So red is what you expect, but you don't expect a green thing, right? So this technique, this diffusion imaging, it provides you information, more specific information about the white matter organization. And not just in healthy controls, but also in pathology, this can be quite useful. Okay, so we basically use this to unravel the connectome, the connections in the brain. And to do that more quantitatively by instead of just looking at it and interpreting the color, we can actually piece together the different ellipsoids. So this is what we basically do. We reduce the information with its dominant orientation. And these little lines, these discrete elements of orientation can now be pieced together. And this is something that we were trained of as a kid as well, right? If I ask my kids, start at this point and connect the little dashes, it's easy to do, right? We do exactly the same, but we call it a bit more fancy, diffusion tensor interpolation to reconstruct fiber pathways with fiber tractography. But it's the same thing, right? So if I show you a few examples, seed points, starting points, if you want, we can now start to piece together all these discrete elements in vivo, non-invasively, just with computer algorithms. And then you end up with these virtually reconstructed pathways. And we can continue to propagate through the data until some criteria are met. Like if your diffusivity becomes too high, you're probably veering into the cerebrospinal fluid. There's no pathways there, so stop tracking there. And we can do this now for the entire brain. Okay, you probably don't have the audio, but that's fine. Okay, so this is just to get you an idea of how these pathways are propagating through this diffusion tensor field, right? So at each point, basically the pathway is looking like, okay, what turn should I take? What pathway should I follow? And this can be done now on multiple data sets, on multiple seed points. And then you end up with these kind of colorful spaghetti-like structures, which we would call a connectome. It's basically the entire set of connections between the different brain regions. And obviously keep in mind, this is not perfect. This is not the real connectome, if you want, because we're not looking at axons directly. We're looking at a diffusion process, and we make assumptions how these diffusing molecules are probing the underlying tissue. Okay, so it's not a one-to-one correspondence, but if you look at many of these pathways, they resemble what we know, right? If it looks like a duck, quacks like a duck, flies like a duck, it's probably a duck, especially if it tastes like duck, right? So we can do something what we would call now, in vivo dissection. We can place regions of interest in the brain and interrogate from all the pathways that we computed, which are the ones that go through specific regions. And so for instance, here in pink, these are projection pathways going from the spinal cord all the way to the cortex. If we look at the green ones, you can kind of observe something what we call the Unsen fasciculus, the hook-shaped pathway connecting orbitofrontal cortex with the temporal poles. And it seems to correspond nicely with what we see from in vivo dissections, ex vivo dissections, sorry. Okay, and obviously the nice thing is that it's not just qualitative. We can look at the underlying diffusivity properties and look at, for instance, how these diffusivity properties change as a function of age, for instance, in the normal developing brain. And you can look at how different structures in the brain show different maturational trajectories. Okay, the big challenge obviously is how can we design diffusivity metrics that can be validated, that can be really specific to maybe some pathology of interest, right? So this is one of the main areas of current research. Another application, well, this is then what I would call day-to-day clinical care. If there's a patient with a brain tumor, then obviously if the neurosurgeon wants to dissect it, it needs to come up with a plan. And within this neurosurgical planning, diffusion MRI can be useful because it can provide information about the underlying or adjacent white matter. And so to put it bluntly, if there's two options, two strategies that the neurosurgeon could consider, he can now be more specific at what the collateral damage would be from the different options. Okay, is there going to be motor impairment? Is there going to be some language deficits? These things can now be kind of integrated more clearly in the planning procedure. But also from a neuroscientific point of view, there's a lot of opportunities, and with let's say increasing hardware performance, we can look at higher resolution, we can look at the cortical folding, and we can look at cortical structure, and in this case also depicted with the color information in terms of orientation. But it provides us with a new tool, if you want, to look at the brain's architectural configuration in more detail. So, as a diffusion MRI scientist, life must be great, right? Well, yes, of course, I still got a job, so we're doing something right. But there's so many things that complicate matters. And I said it before, it's not a perfect technology. This fiber tractography, if you look at it, it looks very plausible. You see these pathways and they connect regions that we know from ex vivo dissections and from neuroanatomy, basically. But we make assumptions, right? I mentioned the diffusion profile. I said we can look at it as a three-dimensional Gaussian multivariate, also known as the ellipsoid. You could think of it as an isoprobability function. But in practice, if we look at these fiber bundles like this, it's actually more complicated. This is a Klinger dissection which also breaks down tissue. So subtle connections crossing pathways are not really depicted in this way. And this also holds for ex vivo dissections, right? So we make assumptions. We assume that the brain consists of this kind of network or fiber bundles, but in practice, it's not just this spaghetti-like structure. It's an array of different bundles with different configurations that are not straight at the length scale of a voxel, which is one of the assumptions that we use. These pathways they can interdigitate, they can kiss, they can bend, they can splay. There's many options there. And if you look at this example, for instance, right? This is not a butterfly. It's not some exotic butterfly. This is a micro section in the region of the medulla oblongata near the brainstem. And it's a polarized light imaging microscopy section with the same kind of definition of the colors. Colors reflect orientation, brightness reflects, let's say, white matter axonal fiber pathways. And you can appreciate now the diversity of orientations, the heterogeneity of orientations. And this is a technique, unfortunately only ex vivo, but it has a resolution at the micrometer scale. So if I overlay my voxels with diffusion MRI, I mean, people laugh at us. They say like, whoa, these 1 to 2 millimeter voxels, you can't take yourself seriously by thinking you can capture the orientation of the underlying pathways, right? Well, indeed, looking at this image now, you can say like, well, there's clearly more than one pathway, one orientation of a fiber structure. How can you model that? Well, we can now start modeling these multiple orientations as well. So instead of looking at one fiber population per voxel, as shown in this case with these ellipsoids, you can now look also at something what we call a fiber orientation distribution function, which clearly shows that there's a huge richness that we can now start to see within a voxel where fiber pathways are crossing. This is also something that obviously affects fiber tractography. If you look at one fiber population, and if I look at this mid-coronal section of the corpus callosum, by using the same mid-sagittal starting points to do tractography, in this case, this is based on an assumption of one fiber model. In this case, I'm showing you multiple fiber bundles. And you can clearly see that you get this wide array of pathways that are now also included, which weren't possible to detect, because if you look at the lateral projections part, the ones that go mostly left-right in the brain, these would not be able to cross the cortical spinal pathways that would go up-down. Okay, so the nice thing is that we can use our modeling, or engineering and physics to try to capture these more complicated configurations within the brain. And so nowadays there's hundreds of models, right? And in a way, I've kind of adapted this quote from George Box. So diffusion MRI scientists, like many artists, have the bad habit of falling in love with their models. And this is something that complicates progress. There's now so many models and everybody thinks they've got the best model, but it all boils down to assumptions. What assumptions are you happy with, and in what configurations are these valid, right? And this is something that is also a lot of ongoing research in this area. But there's another quote, which I like. All models are wrong, but some of them are useful. And indeed, like I said, if it looks like a duck, quacks like a duck, flies like a duck, and tastes like a duck, it's probably a duck. So if we do have some in vivo way to capture specific pathways, even though they're not perfect, but have an approximation of it, think of the insulin fasciculus. It's probably not complete. It's not as specific as you would want it, but it gives you a kind of an overall idea of where that pathway is located. So if there's something wrong in this pathway, we can look at it in more detail. And finally, I would like to mention a few recent developments. One is related to, you could call it the Facebook or the Google Maps of the brain. We're looking now at this entire set of connections, right? And we can build up graphs, networks, and look at properties of these graphs, like efficiency or modularity or clustering coefficients, all these properties that we learn from other network science. Think of LinkedIn or Facebook or all these social media things. They literally are based on network theory. And these technology, this knowledge, the algorithms are now being transposed to this set of connections. But there's many, many challenges that we still face. How do we define a brain region? Do we look at cytoarchitectonics? Do we look at functional aspects from, let's say, fMRI or other technology? So these are still ongoing research areas that are very interesting. So still lots of work to do. But you can do more than just the brain, because diffusion MRI is about diffusing molecules. And obviously we've got molecules in other areas of our body. So in this case, what I'm showing you now is part of the sacral lumbar plexus, where we look at peripheral nerves. And so that's also very interesting to see, for instance, looking at the pudendal nerve or the sciatic nerve. In urology, people are very interested in looking at disorders, bladder disorders, etc., and how they are interlinked with peripheral nerves. And a final one, this is even a more exotic one. Take a few seconds to think what this could be. Well, it's not part of the brain. It's not even a nerve. It's actually part of the kidney. These are the medullae of the kidney. And so, people are also very interested in looking at that, from that point of view, from urology, how the different medullae work and looking at properties. So yeah, I mean, anything that has soft tissue and a lot of water molecules, we can start imaging. So we have looked at even the anal sphincter, the female pelvic floor, all the muscle tissue, the heart, but even beyond human tissue, you can look at squids. They've got very nice architecture there, the muscle, the neurons, the big neurons, etc. So there's a lot of opportunities to look at. Okay, I want to conclude by actually thanking all these people and many, many more that have helped me, throughout my career and with all the work that we're doing. So obviously, like I said, if you want to go fast, you go alone. But if you want to go far, you go together. And it's always teamwork, especially in science nowadays. And with that, I would like to thank you for your attention. Kheli Mamnoon, if I'm not mistaken, this is the pronunciation.
Perfect.
But it's a shame it's not live, and I can't get the feedback from the audience now. But thanks for everything. So I'm happy to take any questions, obviously.